Hey there, what's going on? I wanted to talk real quick about ProjectOnPlane, which is a function provided by the Vector3 class of Unity Engine, and what it can be used for in your game development, assuming you're writing your own collision detection or anything of the sort. So here I have an MS Paint diagram, which represents a raycast going out from a particular position. Let's say this is our player down onto a surface like a floor. You may know that the normal provided by the raycast hit, right? That represents a line perpendicular to the surface of what we hit. So you can see this is perpendicular to our floor. It forms a right angle here, and it goes straight out from our floor. If we had a wall, our normal would come out this way, which is super useful because it calculates, for example, we can use that to reflect, to reflect this way. But another thing we can use that for is actually calculating how we can lay any particular vector onto that surface. And what I mean by lay is, let's say we took this raycast and we just moved it, right? And then laid it along here. That's our blue line. That's what ProjectOnPlane does. We can use this normal to take our vector, let's say our raycast here, and we can just lay it down on the floor. I'll show you why that is useful, or at least one reason why that's actually useful in writing our own collision detection. So speaking of writing our own collision detection, here's a very simple function. All this function does is take our movement input vector, so that's our keyboard movement, as well as some other stuff for gravity, etc. Don't worry about that. It transforms it into a world space direction. So you see transform direction from local to world space. And we check in our move body function, which is called every fixed update. We check, are we colliding right now? So we pass in some variables and we say, hey, are we colliding with anything? That's an overlap sphere cast internally. I will show you. It's just an overlap sphere. And we say, hey, are we colliding with anything? And if we're not colliding, we go ahead and move the character. It sounds perfect, right? We take our input vector, we check forward where our input vector is if we're colliding, and if we're colliding, we just don't allow moving to that position. So it sounds perfect, and in a way, it does work quite well. You'll see if I walk up to a wall here. But keep in mind, my character controller is kinematic. That's why I'm writing this kind of thing. It's kinematic, so it doesn't actually interact with normal colliders like your typical rigid body is. This is for people who are implementing their own custom collision detection, but Vector3 ProjectOnPlane can still be used even if you're using normal rigid bodies. Anyway, I'm digressing. You can see we just hit the plane, but the problem is I'm still pressing forward. And I kind of, if you played a lot of old school FPSs or even new school FPS, you kind of expect to slide along the wall here. You kind of expect to kind of go in a diagonal, right? You kind of expect to hit the wall and strafe along it. Now, let's say if I wanted to peek out this wall in an FPS, it's kind of weird. I have to kind of, manually adjust my character's position. And it would be nice if we could just naturally slide across this wall. But of course, we're checking where we're going to collide with. We're finding a collision, and we're just not allowing movement. It's very naive, and it doesn't allow for fluid movement. So let's fix that. Well, sort of fix that. Let's demonstrate how ProjectOnPlane can fix that. I'm going to write a little bit of code. So let's say we are going to collide. We'll write an else statement. And in that else statement, we're going to call a function called surface projection. You can call it whatever you like, but I'm just going to call it surface projection. And we're going to pass in our movement vector. Now remember, our movement vector isn't where we're going to move to. Where we're going to move to is equal to our body position plus our movement vector, just like we're doing here. Our movement vector is a world space coordinate representing the distance we're going to move if you use its magnitude, as well as some other useful things to us. It's representing what our input is in world space coordinates. So we're going to pass that into our surface projection method. Now keep in mind, body here is just referring to rigid body, and a rigid body is using get component. Really, really simple stuff. So let's go into our private void surface projection method that we're going to create. And we'll allow it to have that parameter called movement. So that parameter is going to be a vector3, and it's going to represent the world space coordinate of our movement vector, how far we're moving. And this is really useful for us. So the first thing we're going to do is we're going to normalize that vector to turn it into a direction. So you should know that normalizing a vector simply turns its magnitude to 1. It takes a big long line in some direction, and it simply cuts it down to a length of 1, which makes it a unit vector. And that's great for representing direction without representing length, because anybody can take that direction and multiply it as much as they like in order to achieve a distance. So let's take our direction, and our direction we want to move, direction to move, is going to be equal to that movement vector normalized. Really simple. The next thing we'll do is raycast out in the direction we're going to move. So say we're facing our wall off to a slight angle, we're going to raycast from ourselves out onto that wall. So let's take our raycast hit variable called raycast hit. Of course, you should probably cache this kind of thing. Write efficient code, please. I'm not going to do it for you. And we're going to call a raycast from our current position out in the direction we're going to move. We're going to output the data given by raycast. We're going to pass in a reference to our raycast hit here. That's what the out keyword does in C#. It just makes this a reference variable, a pointer, if you will, under the hood. And our max distance is just going to be our collision cast radius plus 1f. If you're wondering what that is, remember how I said we use an overlap sphere here? That's what's used to determine the width of that sphere. And I'm actually debugging it out. That green sphere, that's what our collision cast radius is. So if you don't have, a code base set up like that, maybe just go with 3 or 4 or whatever suits you really. So what we're going to do is raycast out. And remember, raycast returns a Boolean determining whether or not, or showing whether or not it hit something. So our raycast in this case did hit something. So when our raycast hit something, let's just draw a ray representing the normal of that surface. So we're going to draw a ray from the point that we hit, right? The point that we hit. If I open up my paint, the point that we hit is right here. And we're going to draw a line from that point that we hit up on the normal. So remember, the normal is a direction. It doesn't really care where its origin is. It could be over here, but our normal always points this way. That's what's important. So let's draw from our raycast hit point to our direction of our normal. Raycast hit dot normal. Super simple. The normal of the surface the ray hit. This is so useful for our project on plane, trust me. We will make the color red, and we're not going to give it a duration. I'll go ahead and play the game, and I'm just going to show you that it looks exactly like our MS Paint diagram. We're going to move out in this direction, and as you can see, we have a red line pointing out from the surface of our plane. Notice it doesn't change in direction. It is always the same direction. I'll go ahead and make this wireframe to make it more obvious. It doesn't change in direction. It's always pointing out from the surface. If I move over to this one, let's move over, oops, sorry about that. Let's move over to this wall here, and I'll show you that no matter where we are, it always points out. The reason it's snapping like that is because I'm hitting the D key on my keyboard, so it's changing where we're raycasting from, because that's our movement vector. It's always pointing out from that surface. So this is already useful, of course, but we're going to use that for our project on plane method. So let's write some code that allows our character to slide along the wall. What we're going to do is lay the line between our current character and the position we're going to move to. So in other words, our movement vector. That's a line pointing in the direction we're going to move to. We're going to lay that along the surface, right? So we're going to lay that line along the surface. So let's take our Vector3 projected, and we're going to set that equal to the result of a Vector3 ProjectOnPlane function call along the line of our movement, taking the normal of the surface that we hit with our raycast. So remember, taking the normal of the surface we hit, taking our movement vector, and laying it down. Now, what we're going to do is then prove that this works by drawing another ray. So following the beautiful MS Paint diagram that we have, we're going to draw it from the point that we collided with, just like our other vector, but we're going to, instead of using the normal, we're going to use the projected plane. And I'll show you that this works by making it blue, just like our other line. Remember, our line is blue, so this is our normal here is, actually normal should be green to match the MS Paint diagram. So our normal is going to be green, and our project on plane is going to be blue. I'll go ahead and play this for you and walk up to the wall. Oh, which wall is it? I think it's this wall. No, it's not that wall. It's this wall. Okay, let's walk up to this wall. And you'll see it's very, very subtle because remember, it's a normalized vector. It's only going to be the magnitude of 1. Do you see the little blue line? Right here, right here. Do you see this little blue line? Watch as I move across this way. The line switches which way it's going. So as I collide into the wall, the line is laid across this way. Really, really useful. Super duper useful. You can see the line is laid across this way. And now that's just the direction we're going to move. That's the direction we're going to move. So literally all we have to do is call body dot move position. Oh, I'm not having a good time today. Move position from our current position plus a projected line across the surface. And of course, you could multiply this by the movement speed of the character. You could do whatever you want with it, but it's just to prove a point, just to prove a point. What you're going to do is you just want to walk into the wall at a particular angle, and you will see, look, I slide across the wall now. And you can actually see if I move my camera down a bit, hopefully I can do this without breaking everything. I'm just going to move my camera down a bit so it's... Speaking of not having a good time today. There we go. That's the one. Okay. We're going to move our character down a bit, and you should be able to see the line now. There you see the blue line moving across the surface. We now slide naturally across the surface. If I move over to this plane here, you'll see the blue line dictates which way we should go because we're laying our movement vector down onto the surface we're colliding with. And look, we slide across the wall. Perfect. That is why project on plane is useful. And remember, you don't just have to apply this to a wall. It could be applied to a sloped floor. Now, of course, my code won't work for a sloped floor because we're casting out the direction we're moving in. You'd need to cast it down onto the floor itself. But it's the same exact principle. All you would need to do is take the surface normal here. So the surface normal is going to be a line going this way because that's, if you were to lay this flat, this would be a line going perpendicular. So it's going to be going this way. And then you use that surface normal from your raycast to lay a line, your movement vector, along the slope. And now your character will handle slopes. Because, of course, my character doesn't handle slopes right now. He just stops if he hits anything. So if I try to walk up this, I just stop. And that's exactly how I've programmed it. All you need to do is lay your line down. Very, very simple. So that is why you should, for your own collision detection stuff, understand what project on plane does. I really hope that helped you and it didn't bore you to tears. Thank you for watching.